the first chapter of our book does motion diagrams. So to give you an example, I'm very artistically challenged, you'll find. I apologize. I do the best I can. Art's not my forte. So let's say we have a car here. This is time equals 0. At time equals 1 second, the car's here. At time equals 2 seconds, the car's here. Time equals 3 seconds, the car's here. Ugly. So the car started down there on the left. It obviously moved to the right. Since as time goes on, it's further and further to the right. What can you tell me about the motion of this car?
Speeding up and slowing down.
Speeds up, then slows down. What tells us that it's speeding up?
The distance.
The distance. In the first second, it only travels this far, but in the second second, it travels that far. If you're going to travel farther, then you have to be moving faster, right? If we wanted to draw in a vector that represented velocity, we would draw an arrow to the right, because that's the direction the car's headed. In the first instant, we would draw it relatively short, because it's not moving very fast yet. In the second case, we would still draw it to the right, but we would draw it longer, because it's moving faster. Then we would draw it even longer, because it's moving faster. But from here to here, well, it's about the same distance, if not a little bit smaller. So the velocity vector, how should it compare to this?
Shorter.
A little bit less than this one. And again, shorter distances, so our velocity vector should get shorter and shorter and shorter as it slows down. In each case, the vector points to the right, though. And that's because the car is moving to the right. As the car moves to the right, its velocity has to be pointed to the right. But the acceleration vector, since the car is speeding up here, what direction is the acceleration vector in? To the right. It's in the same direction as the velocity. But over here, when the car starts slowing down, the acceleration vector is to the left. Okay with that? What would the picture look like if the car went the same speed the whole time?
Equal vectors.
There wouldn't be any acceleration. What would be equal vectors?
The direction would be.
So the velocity vectors would all have to be equal. There would be no acceleration. If it traveled along that straight line at the same speed, so constant velocity, then acceleration would have to be 0. Straight line, constant speed means constant velocity, because you're not changing speed or direction. So the picture I'm going to get lazy here.
Would there have to be an initial acceleration?
Well, if we're already looking at a time when it is moving.
Okay.
Only if it was 0 to begin with. So we're looking at it at an instant when it is already moving. So I'm getting lazy here. My car has now become a ball. They're easier to draw. Every single velocity vector would be the same. They're all pointing to the right because that's the direction the car's moving. They're all the same length because it's traveling at the same speed at every instant. The distance between each consecutive ball is the same. So the acceleration is 0, specifically. 0 acceleration means your velocity is not changing. Doesn't mean you don't have a velocity, just means it's not changing. So what would the graph look like throwing a marker up? Or if I had a ball, throwing it up. What would the picture look like? So if I start it here,
Speed up, slow down, and speed up.
okay, let's start it as it leaves my hand.
It'd slow down the whole time, but it'd start high.
So it'd start with a big velocity, but then the velocity would get smaller. And smaller. Until at the instant it's at its highest point, the velocity is 0. Are you okay with that? At that instant, the highest point, the velocity is 0. So what can you tell me about the acceleration at that point? So many ideas. What is the definition of acceleration? Change in velocity. If my velocity at that instant were 0, and the acceleration was 0, what would happen? Not a darn thing. It'd stay there. If it doesn't have an acceleration, its velocity could not change. So it'd have to stay 0. Well, obviously, our markers don't hang out and stay there. So there is an acceleration. That is an example of when the velocity is changing direction. It was headed up, is changing direction to be headed down. Some question?
For a split second too?
No, it's not. In fact, the whole time, the acceleration is constant. For the entire time, the acceleration is pointed downwards. Has to be pointed downwards in order to slow the ball down as it goes up. Has to be pointed downwards in order to speed the ball up as it comes back down. It's downwards as the ball changes direction from going up to going down. This is the acceleration of gravity. It's constant. It's always pointed down. It has a value of approximately 9.8 meters per second squared. It's negative because it heads downwards, points down. That's why as objects move up, they slow down, because the velocity is opposite the acceleration. As they turn around and head back down, they speed up. The velocity and acceleration are in the same direction. Anytime the velocity and acceleration are in the same direction, your object will speed up. Anytime they're opposite in direction, it will slow down. Okay? So that's a tricky one. You can, at that instant, have a 0 velocity, but a non-zero acceleration.